Hi, I'm Jack, and I'm going to be demonstrating how to find the optimal class schedule for your program of choice using linear programming. Although we'll be focusing on one dataset in this video, my objective is to create a generalized method that can be used for any academic program starting at any point in your college career. We are going to demonstrate the formulation with a familiar dataset, the classes and requirements of the data analytics major. Some assumptions that we have are that we will be starting at the beginning of freshman year. There will be credit for Math 1150, but not Calc 1 or Calc 2 or any other AP credits. Although most people do come in with some AP credits, the credits that people have are varied, so we don't want to make any other assumptions there. Here's the general formulation. This is a mixed integer linear program with lots of binary variables. In fact, all variables outside of the objective function are binary. I'm going to briefly go over the key variables and constraints in this formulation to create a better understanding of the problem. The bread and butter of this formulation is the set of binary variables that indicate a class was taken on a particular semester. The C subscript indicates the class that X is representing, and the X subscript represents the semester the class is taken. A value of 1 is assigned to X if class C is taken on semester S, and otherwise the value is 0. The range of S in this particular example will be 1 through 8 since we are assuming freshman status and a 4-year graduation plan. Finding the optimal values of these variables in the GAMS output will give us a set of classes in the optimized schedule and what semesters they are taken in. Here we have some simple constraints for credit hours. The first makes sure any given semester the credit hours taken are between 12 and 18. The second ensures that there is enough total credit hours to graduate. The values are constants representing the credit hour value of the corresponding class. These constraints enforce some rules about when a class can be taken. The first ensures that all required classes are taken at some point. The second is for when two classes can fulfill the same requirement. And the third ensures classes that are only offered certain semesters are not put on our schedule during the wrong semester. We need to modify these constraints for optional classes. Using the auxiliary variable y, we allow optional classes to be taken either 1 or 0 times. This auxiliary variable will be helpful in the next set of constraints. These are the constraints for prerequisites. These are the most restrictive constraints and will determine the final optimal schedule more than any other constraints, save the requirement constraints. For required classes, prerequisites are straightforward to formulate. We just need to ensure the semester subscript for a prerequisite class is less than the subscript for a class that depends on it. For optional classes, we need to relax the prerequisite constraints when a class is not included in the schedule. We also need to make sure that if a prerequisite class is also an optional class, that it is included in the schedule at some point, or else the prerequisite constraint is meaningless. Gen Ed requirements are the simplest because they can be generalized. Instead of these variables corresponding to classes, they correspond to a particular GE category. We just need to enforce that the sum of all the variables from one category is the same as the number of classes required from that category. To represent specializations, we will use compound alternatives. Auxiliary variable Ri represents specialization I and is set to 1 if that specialization is chosen. Exactly one specialization should be active at a time. Inside each region, we have constraints for required classes and credits for the corresponding specialization. And finally, we have the objective function. The objective is simply to minimize the sum of the delta values for each semester S, where delta S is the absolute difference in credits taken in semester S from 15. To formulate an absolute value for each delta S, we use two inequalities. The first handles the case that credits taken in semester S exceed 15, and the other if the credits are below 15. These inequalities converge when the credit hours taken is exactly 15 for one semester. For any given credit hour value, one equality will represent an absolute difference and the other will be a redundant constraint. Because we are minimizing, we do not need any other restriction on these delta values, as minimization will always push the value to a positive integer value given these inequalities. Here's a snippet of some of the GAMS code. As you can see, there are hundreds of variables involved, 8 for each class, and some other auxiliary variables, and hundreds of constraints as well. I actually wrote a script to make the GAMS file because I was afraid I would get carpal tunnel syndrome typing it manually, so that was much easier. So here are results after running the GAMS code. Unsurprisingly, the computational specialization was the most efficient track through the program, which is the specialization requiring the fewest credit hours. The results aren't particularly exciting here. This looks like a typical class schedule for any DA major in the specialization. This is likely because the DA major is restrictive in course sequencing and has many core requirements. I use this data set for demonstration because we're all familiar with it, but this method would be much more insightful for less restrictive programs or starting from some semester after the fall of freshman year. Okay, now some final thoughts. Now there are some drawbacks to this method. This method doesn't take into account class difficulty and is likely to give you a semester or two just full of hard classes that you would never want to schedule yourself. Also, it doesn't really care about your specialization focus. So if you wanted to be in, let's say, the machine intelligence focus in the computational specialization, it doesn't really care about that. It's just going to take whichever classes in this specialization fulfill the credits the easiest. There's also hundreds of variables and constraints, which makes this formulation a little bit impractical instead of just doing it by eye. Some possible solutions to this. We could make an objective function that takes into account difficulty rating as well. I haven't formulated this, but I think it would be pretty straightforward to do. For specialization focus, we can make a double compound alternative. And to make the formulation a little bit easier, we can automate the formulation with a script, which is what I did. And that would make it a lot easier to reformulate this maybe every semester, given maybe you didn't pass a class or maybe you didn't get into a class you would think you did. So you have to go back and re-optimize and see what your optimal schedule is at that point. The best uses for this are probably not starting from freshman year. They're probably for people who are switching majors, programs with lots of open options, and maybe making your own custom constraints where you say you want to take this class then in this semester, another class in another semester, and so on, and then seeing if there's a feasible solution for this. Again, my motivation here was to create a generalized method that anybody could use in any program to find an optimal class schedule. That's all I have. Thank you for listening.